Hello, my name is Shivda, and today we're going to look at a simple probability problem. It's not very complex, but it has a very interesting, the result is very interesting in that it leads to something connected with some really complicated math and some famous results, which I'm sure you've heard of. But anyways, let me phrase the problem. There are two baskets, A and B. Each contains the same number of balls, say B balls, which are either white or black. So they only contain white and black balls, B balls. White, black, white, black. And now the idea is that we draw n balls from each urn, where n is greater than 3. Actually, I'll tell you what, let me just say. Draw n greater than 3 balls from each urn with replacement. In other words, we draw the ball, replace it, draw again, replace, draw again, replace from each urn. We do that 3 times for each urn. And the question is to find n and the composition of the two urns. There may be many answers to this, but find n and some composition of the two urns. In other words, number of white balls, number of black balls, number of white balls, number of black balls, such that the probability of drawing all white balls from the first urn is equal to the probability of drawing either all white or all black balls from the second urn. So such that probability all white, and this is for the first, is equal to probability for the second urn, all white or all black. So before we go on, internalize the problem carefully. Let me repeat the condition once again. There are two baskets, two urns, containing only white and black balls with the same complete number. In other words, both have B balls. They can be distributed between white and black balls in any way. And we want to draw some number of balls from each urn, some number n, where n is greater than or equal to 3, such that the probability of getting all white balls from this first urn is equal to the probability of getting all same colored balls from the second urn. And the same colored balls could be all white or all black. So this seems like a well-defined problem. And in fact, more than well-defined, this seems like, there's some degree of the freedom that you have. It's asking to find n, and it's asking to find any composition. It seems like this problem would be, a little hot. The problem would be narrow. The solution would be narrower if n was fixed. So you had to draw 5 balls in replacement, find a composition such that this condition would hold. But it still seems like a very well-defined problem and something that's solvable, right? Something that has a solution. Isn't there some possible composition such that the probability of drawing 3 balls, let's say n is equal to 3 from this urn, is equal to the probability, 3 white balls from this urn is equal to the probability of drawing either 3 white balls or 3 black balls from the second urn? Isn't there some composition? It seems like this should have an answer. It turns out that it does not actually. But to figure out why, let's get into the math, let's do the algebra, let's approach it in a logical manner and see what we get at. So I hope you've internalized the problem, because I'm going to erase this stuff at the bottom. Alright, so let's assume we have Z white balls in the first one, X white balls in the second urn, and Y black balls in the second urn. And the total number of balls is B. So in other words, rephrasing the problem, what we want is the probability of drawing n white balls from the first term. In other words, z divided by b to the power n. The probability of drawing one white ball from the first term is z by b, the total number of balls. And we replace it and do it again and again n times. So the probability of drawing n white balls is z by b to the power n. In other words, we want this probability to equal x by b to the power n, the probability of drawing n white balls from the second urn, plus y by b to the power of n, the probability of drawing n black balls from the second urn. The or is a plus. You can have this condition or this condition, so the probabilities get added. So in other words, this is the equation we want to solve. We want to find some n and some composition. In other words, some x and y and z, such that this holds. So it seems like we're given very little restrictions. We have a lot of freedom in the problem. Yeah, we really have no restrictions at all. But what does this simplify to? So we know that b is nothing but x plus y, right? Because b is the number of balls, which is the same for both urns, and x plus y, white plus black, equal to b. So we can replace b with x plus y. X plus y. X plus y. And you know what? I didn't even have to do that step. That was unnecessary because that x plus y, that b at the bottom, is going to cancel out. If you multiply throughout by x plus y to the power n, you would have z to the power n equal to x to the power n plus y to the power n. And does this look familiar to you? This last equation, does that ring a bell? This is nothing but Fermat's last problem. Fermat was this French mathematician who in one of his notebooks, one of his diaries, claimed that this equation has no integer solution for n greater than or equal to 3. And the reason it's such a famous problem is that he scribbled in the margin of his notebook that he would prove it if he had time, but the margin was a little too small to contain his proof. He claimed he had a very simple proof, and that was a trivial result. Many mathematicians disagree and thought he must have overlooked something, because for years and years and years this problem remained unsolved. Till finally Andrew Wiles of Princeton, after 7 years of hard work and actually coming up with an incorrect solution, went back, worked on it for more, and finally came out with a solution to prove that this is no integer solution for n greater than or equal to 3, which used huge forms of complex math. It was this amazing project, long, complex. Proof was over 200 pages, understood by only a handful of people in the entire world. So it would be really amusing if Fermat did indeed have a solution. So given Fermat's 200-page proof, plus page proof, 200 plus pages, this problem is really equivalent to solving this, and we know that then this does not have any solution. Which is really interesting, because you can actually see how a problem this is one application, so to speak, of Fermat's last theorem. Some real-world problem which really on the face of it seems so solvable, like it has to have a solution, especially since you have so many degrees of freedom. It seems like there's very little restriction imposed on you. And yet it just does not have a solution. For n equal to 2, these would be simple Pythagorean triplets. So 3, 4, 5, for instance, 5 squared is 25, 3 squared is 9, 4 squared is 16, 16 plus 9 equal to 25. There are plenty of solutions. There are infinitely many triplets. You could just keep multiplying 3, 4, 5 by some multiple, and it would work out. But yeah. So I thought it was fascinating how a real-world probability problem, which seems so solvable, actually, a la Fermat and Andrew Wiles, just can't be done. Thank you.